Welcome, folks. So I want to thank everybody for coming to the Flash Memory Summit. You know, this is going to be our largest of these events yet. We think there's going to be over 6,000 people that would have registered for the 2015 Flash Memory Summit. And that's thanks to all of you who are here, and thanks to our exhibitors and everybody else who played, all of our speakers and everybody else who played a role to make this event what it is today, our advisors, all this group. So just want to let you know that, and we really appreciate that. And just the number of people that are here in this room shows the attention we've got. And it's a great pleasure this year to be able to announce for our first of several keynotes that we'll be having today and the next couple of days, Hideo Inoue, who is the general manager for the Advanced Vehicle Research Project with Toyota in their Future Projects Division. He also is a visiting professor rather, at the Department of Mechanical Systems Engineering for the Tokyo Institute of Agriculture and Technology. He was a recipient of the National Transportation Safety Award in 2009, and it's a great pleasure to have him talk to us today. He's got, by the way, he also will show some interesting views of early safety issues with some of the first transportation vehicles. Having seen his video, I'm looking forward to that. So with that, I give you Hideo Inoue. Thank you.
Thank you.
Thanks.
Thank you for the introduction. Good morning, everyone. My name is Hideo Inoue from Toyota Motor Corporation. I'm a great honor to have this opportunity to give a presentation at this conference. I'm very happy to be here. The title of my presentation today is Driving Intelligence for Safer Automobiles. Okay. First, let me look back at the history of vehicle safety. The world's first vehicle was a steam-powered vehicle invented by Nicholas Joseph Cuno in 1769. Let's watch an interesting video. Couldn't steer or stop and crashed into a wall because the front steam iron pod was too heavy. This shows that safety was a significant issue from the moment that the vehicle was born. Today, pre-collision systems are an example of modern safety technology. Toyota has already released the latest PCS in the Lexus LS and other models. This PCS uses a stereo camera, millimeter wave radar, and near-infrared light. It works even in adverse weather and at night. PCS warns the driver when it detects a pedestrian or object, and then activate automatic braking. This graph outlines the recent and future trends of safety technology development. The first category is damage mitigation technology based on passive safety. Second category is collision avoidance technology based on active safety, including rear end and pedestrian collision avoidance and lane departure prevention. This technology includes automatic emergency braking, electrical stability control system to prevent skids, and so on. These technologies help to prevent accidents at the last second before a collision occurs. Now, I want to think about concepts that can help to reduce accidents further. We have learned that human error-induced accidents account for about 90% of accidents. To help prevent these accidents, it is important to reduce the risks in normal driving. Therefore, In the next step, it will be necessary to reduce accidents caused by human error more directly. Expert drivers predict risk in advance and adjust accordingly. To make vehicles more intelligent in the same way and to reduce the driving risks, Toyota has been researching and developing intelligent driving technologies since the early 1990s. We increased the scope of our R&D efforts from the middle of the 2000s. First, we identify how close our existing dynamic control technology is to ability of a highly skilled driver once a driving path is determined. This verified the feasibility of a basic steering, braking, and acceleration functions, as you can see here. Second, we are testing sensing and recognition technologies on public roads in US and Japan. This video was recorded in Tokyo. We created 3D spatial maps using a 360-degree scanning lidar while driving. Then we localized the surrounding environmental model, localized using a spatial world model and sensors to enable automated driving. Based on this background, I'm going to talk about these two important topics. First, driving intelligence for elderly drivers. As Japan's society ages, we need to show our sincere approach to this serious problem. One of the causes of accidents involving elderly drivers is decrease in physical skill. Figure 1 shows the reaction of drivers to a forward collision warning using the Toyota driving simulator. The older the driver, the higher the ratio that could not recognize the warning. On the other hand, elderly drivers want and need an active life. Therefore, mobility is necessary to improve their quality of life. Advanced driver assistance system, ADAS, with driving intelligence is designed to compensate for the decline in physical ability by adding an intelligence model. Based on this background, we have constructed a model of an experienced expert driver who drives safely and smoothly. Through this shared control concept, we can compensate for the decline in the driving performance of elderly drivers. Experienced drivers take into account information about a predicted horizon about 10 seconds ahead. In phase 2, the prediction of hidden risks between phase 3 emergency avoidance and phase 1 normal driving is important. The predicted information is obtained by direct sensing and by knowledge-based information. Through the anticipation of the future situation, a driver assistance system that avoids a collision at the last second based on only sensing cannot realize zero accidents. We are working on the new phase of driver assistance technologies which can learn the anticipatory driving of expert drivers and then become more intelligent. This figure shows a structure of driving intelligence model. First is the normal driving control, which can trace a desired path and following the proceeding vehicle at a safe distance. Next is the risk potential-based control to mimic driving that anticipates hazards. We will add the knowledge-based behavior here. Finally is emergency avoidance control for preventing accidents as the last second. Conventional active safety systems are integrated at this control level. First, we are studying integration of the risk potential field at the normal driving control level. An example of potential field is shown in the corner. Here is an example of the potential when following the proceeding vehicle. This one. The logic is used as a dynamic potential field. The video shows a typical driving scenario that requires hazard anticipation. In a case like this, when there are pedestrians coming from the space behind a stopped bus, collision avoidance based only on a sensing system cannot avoid the collision completely. We need to add defensive driving behavior and anticipate the risk in the way that an expert driver does. The second part of driving intelligence is risk potential-based control. As you saw in the previous slide, we can anticipate future risk in hidden areas that cannot be directly detected by sensors by introducing the concept of potential field. Under this concept, the vehicle can reduce its speed to a safe level while overtaking the stopped bus. As a result, it can avoid a collision even if a pedestrian appears. We observed expert drivers always drive in this manner. To make a safe system, we need to introduce such physical models in the normal system. Now, I'd like to show a demonstration using a real car. Driving intelligence is demonstrated here by a Toyota Prius test vehicle. This vehicle has three main algorithms, as I explained. The first is normal driving control. The second is risk potential-based control, including hazard anticipation. The third is the collision avoidance model by braking and steering. I will show you a video. The automated driving Prius predicts the hazard in advance based on the position of the parked vehicle by risk potential algorithms and reduce speed automatically. If the vehicle evaluates that the risk is getting lower, the vehicle will accelerate again to the cruising velocity. The video on the right is a test case in which a pedestrian darts out from the space behind the parked vehicle. The automated driving Prius can avoid the pedestrian easily by implementing a hazard anticipation speed control in advance to reduce future risk. The result and its control effect very simple. This was achieved by embedding driving intelligence inside the ADAS. This slide shows the effect of the defensive driving by driving intelligence, as you saw in the previous video. We can see from figure 1 on the left the system can control speed in a similar way to an expert driver. And as shown in Figure 2, by introducing defensive driving behavior into the collision avoidance system, we can handle critical situations over a wider range as the vehicle slows down its speed in advance. If the vehicle can operate like this, it can prevent human error like carelessness in driving. We want to use this useful driving behavior in the design of the co-pilot system. Finally, let me show you a demonstration of an emergency braking and steering control system for pedestrian collision avoidance. The new this PCS with steering assist can help prevent collisions in case where automated braking alone is not sufficient. This is a system determines that a collision cannot be avoided by braking alone, and there is sufficient room to avoidance. Steering assist is achieved. This slide shows a conceptual diagram of the ADAS with driving intelligence. Driving intelligence consists of three main controls. First, the sensor fusion and world model consists of perception and cognition models based on automated sensors and map data. Here. The second, the motion planning algorithm here ensures smooth and safe driving by integrating the risk potential, normal driving, and emergency avoidance parts. Third, shared control here. This performs seamless override of steering, accelerator, and brakes, and the handover control of the driver's system interaction. This is a more logical structure than conventional driver assistance systems and can be adopted for automated driving. We are currently developing recognition technologies for various driving conditions. This slide shows an example of the fusion of camera and scanning LiDAR sensors. This sensor fusion technology generates driving paths centered on the driver's vehicle. This is an example of scanning LiDAR. This technology learns robust driving paths while referring to external map data to create route map models for the vehicle. Another point, pedestrian detection is another issue. Let me show you a video of pedestrian motions detected by a prototype scanning LiDAR developed a few years ago. We want to improve pedestrian detection capabilities by using LiDAR and camera technology. Additionally, the previous slide showed an example of 8-line LiDAR. This slide shows a 3D LiDAR system currently being developed. This system is capable of robust detection based on 3D spatial models. We are also aiming to make it small and inexpensive to meet vehicle installation requirements. Next, I will introduce some current developments for handling traffic congestion and highway driving intelligence. Traffic congestion usually occurs at some points which are slight changes in load gradient. We are aiming to realize a traffic environment with no congestion or accidents and low CO2 emissions. Here, systems such as adaptive cruise control or ACC, cooperative ACC, and automated highway driving will be effective, very effective. I will introduce our cooperative ACC. Vehicle-to-vehicle communications has been added to adaptive cruise control with millimeter wave radar used to maintain the distance between the vehicles. Acceleration data from the vehicle in front allows the following vehicle to adjust speed automatically, accurately, and steadily before the distance between them changes.
Cooperative Adaptive Cruise Control is a system that combines adaptive cruise control with intelligent transport system technology and inter-vehicle communications. Cooperative Adaptive Cruise Control allows the sharing of acceleration and deceleration information between vehicles, and it can achieve even higher precision control through coordinated acceleration and deceleration and constant distance control. The system maintains a constant distance from the vehicle ahead by synchronized accelerating and decelerating. Cooperative Adaptive Cruise Control uses inter-vehicle communications to achieve smooth driving conditions with no delay and minimal time lag when decelerating or accelerating.
Okay, this graph shows the steering stability performance of ACC and cooperative ACC compared to human drivers. ACC reduced the amplification of the braking shock wave here. Cooperative ACC changed the amplification of the shock wave by improving the damping of speed control maneuver here. From this slide, we can see the traffic jams can be reduced by half with an ACC penetration rate of 20% and an amplification rate of 0.98. We are testing systems aiming at these targets. Finally, I'd like to focus on a system called Automated Highway Driving Assist, or HDA. I will show you a video.
Toyota Motor Corporation is researching automated driving technology and aiming for an early rollout of the intelligent driver support system that assists drivers to react more skillfully in any situation. We aim to realize a prosperous society where everyone can use cars safely and comfortably. The new Automated Highway Driving Assist, AHDA, is our proposal for using automated driving technologies to make everyday highway driving safer and more comfortable. Longitudinal control by Dynamic Radar Cruise Control, DRCC. When the driver activates the system, the DRCC starts controlling the vehicle's speed and headway. The DRCC uses the millimeter wave radar mounted on the front grille to maintain a pre-selected headway to the preceding vehicle. Lateral control by Lane Trace Control, LTC. LTC enables the vehicle to smoothly trace the appropriate path in the current lane by recognizing lane markers and preceding vehicles, and with steering control. LTC, combined with DRCC, makes it possible for the driver to enjoy safe and comfortable highway cruising. Real-world conditions like deteriorated pavement, faded lane markers, and exit-only lanes, however, may hinder AHDA's performance. Predictive and Interactive Human-Machine Interface, HMI. Preview HMI predicts these challenging scenes using enhanced map, then informs the driver in advance. For example, when there is a merge ahead, an icon is displayed on the monitor so that the driver can take action in a calm and safe manner. Preview HMI is able to predict challenging scenes the AHDA might have difficulty with and relay that information to the driver with ample time to take action. The HMI monitors driver status during AHDA operation. When the HMI detects driver inattention, driver's hands being off the steering wheel for a prolonged period, or any sort of unsuitable circumstance, the system will prompt the driver to take action. This advanced HMI in AHDA encourages two-way interactions between the driver and the vehicle system to provide smooth transitions between supported and manual driving. Toyota continues our efforts to realize safe and comfortable transportation without traffic accidents by creating these state-of-the-art automated driving technologies.
This system will launch in the near future. Additionally, this is our latest test vehicle that we are using in driving evaluation at our Higashiuchi Technical Center in Japan, and as well as our US Technical Center. It consists of a robust configuration of sensors, including LiDAR at the front, rear, and sides, and a front-facing stereo camera. We are using this prototype vehicle in our day-to-day research and evaluation of key highway driving scenarios, such as merging, maintaining in lane position, overtaking, and turning off, and so on. Okay, I would like to show this slide to conclude my presentation. Firstly, I believe that the vehicle evolution will include driver assistance and the autonomous driving intelligence of an expert driver. ICT technologies will then link to this, so that external information can be used when needed and fed back to the vehicle dynamically. By repeating the development process like this, the triad of vehicle, driver, and road intercommunication will become more intelligent, leading to innovative progress in both traffic environments and in individual driving, similar to the evolution of an ecosystem. We are aiming to establish this cyber-physical system to achieve human-centered innovation of mobility. It is truly my dream. Finally, I'd like to discuss our aspirations for non-volatile memory. For engine, body, and chassis systems, we must improve aspects such as reliability, cost, and writing speed. For example, flash memory must be reliable at least 10 to the fifth times and have a retention period of at least 20 years. We need to improve instruction fetch and data read and write performance response, and to reduce the sleep wake-up power. Further requirements for driving intelligence include a similar capacity as PC for machine learning of each model, like sensor fusion model, motion planning model, and driver model. One example is intelligent map model data localized on the driver's vehicle. A vehicle can easily validate data in the real world. The result of this validation can be used to construct even more reliable learning models. Non-volatile memory will play a more vital role in this. We are looking forward to the evolution of non-volatile memory technology from the standpoint of the vehicle ecosystem as well. Thank you for your kind attention.
Thank you. And if you did have any questions, I know he's going to be around today and I think tomorrow also, right?
No, okay.
And there's a Toyota car that will be in our exhibit area, so he will be around there if you need to get a hold of him tomorrow. Thank you very much. Maybe we go this way.